So does that look good? Can everybody see that? Great. Um, so a brief history of computation. I often find when I'm learning about something that understanding how we got here, and the whys of how we got here, are sometimes very important for understanding, why the world is the way that it is. The world is a continuous Markov process, and the change from now to the next state, is dependent on the state now. We step into the next state, and the state beyond that is dependent on the state there. And so, looking back at the history of the process can sometimes give us insight into, how we got where we are, why we are where we are, and etc. Um, so why do we even care? Why are we studying computer science? Fundamentally, with a quick quote from Marx, the point is not to understand the world. The point is to transform it. And this is, I think, one of the great powers of computer science is. I mean, compared to some of the other sciences, and with no disrespect to the other sciences, the geologists aren't out there producing new rocks. The those folks that study plate tectonics aren't creating new continental plates. They aren't creating new earthquakes. So computer science and mathematics and statistics are a little bit different to studying the world. This is how we learn how to change the world. um, Most of this presentation, I have to admit, I stole from a lecture that I used to give at San Jose State. It is, however, changed from programming paradigms to computation in regards to the modern distributed computational model. So the first counting device, very simply, are hands. And without getting cute, we've got five on one hand. We can get up to 10 with two. If we start with knuckles, or with our knuckles on the fingers, we can get up to 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We can even do binary on our fingers, and I will avoid doing that because when we get to 4, that becomes a rather rude gesture for me to be using at work. Um, so just using the body. I mean, this is the first obvious counting device. Once we move beyond, just using our fingers and our toes and whatnot, we need something to help us keep track of what's going on, and what we need something to be able to record. How much we've counted, and we can take that and keep it over a certain amount of time. So we add data storage. And the first data storage that we encounter within human history is the tally stick. You know, we take a stick, we cut a number of lines across it, and that's how many sheep we have, right? If I can count the number of sheep and it matches the number of tallies that I've got on my stick, we know that we haven't lost any sheep. We've got data recorded, we've got it persisted. This is a very important step forward. And as it's been said, repeatedly, I mean, to do most of mathematics, all you really need is a piece of charcoal, a couple of operators, and something to write on. Piece of paper, large bit of bark, cave wall. Um, this is all fairly easy to get. So once the idea of numbers comes along, we can come up with the idea of addition. You know, I've got 3 sheep. There are 4 sheep over there. Together, we've got 7 sheep. That's the addition operator. I've got my 7 sheep. Some wolves came along and ate 2 of them. Right. So now I've got 5 sheep, and we've got our subtraction operator. And with these operators, from addition to subtraction, we can start to learn about multiplication. From multiplication, we can start to learn about division, and the rest of mathematics continues off of there. I mean, there's obviously a couple more concepts that are useful, like zero, but those come in a little bit. In fact, here. So the formalization of numbers allows for more complex arithmetics. Um, if we take a look back to say Roman numerals, those are actually rather difficult to do very complex mathematics with. And so when we start using the Hindu-Arabic numbering system in the base 10, we find that this becomes a very natural, very useful numbering system that allows us to push our mathematics forward. We can write it all down. It's all standardized. We can hand it back and forth. I can write 10 plus 2 equals 12. I can hand it to you. You can understand it. This allows for communication between people. It allows for persistence, and because of the standardization, I can look back to a document written 1,000 years ago. If it's using the Hindu-Arabic system, I can understand it. Um, but importantly, when we're talking about computer science and when we're talking about computation, the numbers themselves aren't actually the important part. And this is probably going to become a repeated sort of theme that I go about. As Hamming said, the purpose of computing is insight, not numbers, right? It's not actually the numbers on the screen that are interesting, right? Taking a look at the screen, we've got a bunch of numbers that are expressed as different light levels and different colors, right? And so when we look at the picture in front of us, we know that that is just a bunch of numbers that are translated into the light spectrum and then thrown up on the screen. It's what it all represents that's important. The number is useful. It's a great tool, but the understanding is what we're actually after. So, what is computer science? Um, Abelson, computer science is not really about computers. Um, it's not about computers in the same sense that physics is not really about particle accelerators. And biology is not about microscopes and petri dishes. And geometry isn't about using survey instruments. The computer itself is an instrument for us to be able to do the work that we actually want to do. We want to be able to understand problems and we want to be able to solve those problems. Right. So, this is, why we're engineers. This is why we do what we do. I mean, this is the fundamental, core bit of neuro. There's a problem. We want a delivery robot to solve it. How do we do that? Right. And so, are we a science? Are we a math? Are we an engineering discipline? I mean, there's arguments for and against, each of those, but fundamentally, it's all right. Computer science is a science. Computer science is very it's the science of knowing what is possible to compute. It's the science of knowing what is possible for humans to be able to accomplish within their own timelines, and it's the science for trying to figure out ways around that. It's a mathematic. We're consistently working with numbers and using numbers as symbolic representations of the things, and it's definitely an engineering discipline. We are continually building new products. We're building new projects. We're writing new scripts. Um, so we're building stuff. So it's all three, and that's fairly important to remember. I'm particularly calling back to the original quote. Um, the point isn't to understand the world, it is to transform it. And this is why I particularly like that quote for computer science, because that's what we do. We understand the world, but then we try and change it. We try and solve the problems that we encounter. So, considering our travels through time and computational devices, going from prehistory and our um, tally stick, the invention of numbers. We get to Babylon and the Babylonian abacus, 2400 BCE. Um, we can still the Babylonians actually were pretty cool. They used a base 60 math system, which it's actually pretty cool for people to be able to use because it has so many different ways to divide it up equally compared to base 10. Base 10 has what 2 and 5. You can split 10 up into 2 and 5. When we get up to 12, we've got 2, 3, 4, and 6. Right, so that gives us a whole lot more different ways to be able to divide things up. Jumping 12 up to 60. That gives us a bunch of ways to naturally divide evenly between sets of 60. So in a pre-literate society, when you're at the market, if you can count to 60, you can then break them off into different units of equal size. Becomes it's a very simple natural operation. It doesn't work so well with writing it down and using it as um, you know as an actual mathematic, but for actual general use, base 60 is pretty cool. Um, so when I first started talking about the anti-Thera mechanism back in 2016, actually nobody knew what it was. They had found it in the wreckage of a cargo ship in the Mediterranean. They dated it to about 100 CE. And nobody knew what it did. I mean, people had some ideas. However, through modern computer science, modern technology, they were able to use imaging, X-ray. I don't actually know exactly which ones they used, but they actually managed to get the parts. They rebuilt it, and they found out that it's actually a computational device. This is a star chart. Um, and star charts, we'll find out over the next couple of slides, are super important. And the reason that they're super important is because that's how we navigate. So if we want to be able to get out into the world, the way that we solve it is we have a map, right? And a static map's cool, but a map that we can actually change into the star configurations for today, that is super useful. That we can use and update daily in order to be able to navigate safely and correctly around around the world, around the Mediterranean. I mean, it's cool stuff, right? Oh, and this one actually was able to track the 4-year calendar of the Olympic Games in ancient Greece, which I think is pretty cool. So, yeah, thank you, researchers, for finding out what we were actually talking about. Moving forward, 200 CE, we have the Chinese abacus. I mean, I had one of these when I was a kid. It's still in use. Um, I forget which of the East Asian countries actually still holds competitions and has schools dedicated to the use of the abacus. Um, but it's very cool. You can actually do complex mathematics very quickly using an abacus. And it's pretty impressive, watching these like kids after they've been through a couple of years of school using them, just go through and ripping apart the mathematics using it. So this is still a very useful computational engine, still in use today. Getting back to navigation, the Astrolab, this is about 1000 CE. I don't honestly remember if this particular model is Northern Mediterranean or Southern Mediterranean. I'm pretty sure Northern, but it's once again a star map. It's a computational map for us to be able to understand where the stars should be tonight. And once we understand where the stars should be tonight, we can use the map in order to be able to navigate safely to our destination. The Torquetum, 1100 CE. Again, this is a star chart um, because navigation is so fundamentally important to trade, to communications, to diplomacy, that you've got to be able to understand where you're going and how to get there. So lots of early computational devices were all around the economic need of trade and navigation and travel. Um, this I absolutely love. So about the same time, 1100 CE, thereabouts, in the Islamic world, they had started to build robots of some fashion. They had robots that could play the flute, but generally as a public service. These scholars managed to put together what they call the castle clock, which is not what we would think of today as a modern wall clock on like the Big Ben or the clock tower of Westminster with the actual clock face and the hands. This is an automated system that goes through and it would ring a bell. at certain points during the day in order to call, the faithful to prayer at the appropriate times during the day, so everybody would know and everybody wouldn't have to worry about it. I mean, this is a grand public service. Jumping forward, once again, lots of mathematical development all through these times, but we're doing a short history. So we're going to jump up to Charles Babbage and the difference engine. So Babbage in England, he built this machine that would do math for us. It's a hand crank machine. You set a couple of switches, you crank the machine, and your answer drops out. Um, Actually, I think one of my favorite little anecdotal stories about the difference engine. Um, and I have a bunch of them involving, British Parliament. But Babbage went to Parliament and a parliamentarian to ask for money to be able to build a machine, and the a parliamentarian said, "Mr. Babbage, if I put the wrong inputs in, will I get the right answer out? Thus showing users have not changed, in the past 200 years since the difference engine was introduced. The difference engine was never actually produced in Babbage's time. The stress tolerances for the required metals just wasn't really available, or it was too expensive. Therefore, it was a theoretical concept. However, in the last couple of decades, one of the museums in London actually built the damn thing. They using modern metallurgical processes, modern manufacturing techniques. They actually built the difference engine, and it actually works. So that's pretty cool. The analytical engine. So this was the second step of Babbage's design. The difference engine was a much more simple machine, even though it had a lot more parts and it was much harder to build. Um, Babbage came up with the idea of a machine that could be used to solve complex equations. Right, big thing. I think this one was supposed to be steam driven, but now we get to meet Ada Lovelace. Ada Lovelace had the brilliant idea to, why don't we have some sort of written input, punch cards or something that we can change, and then every time we do it, we'll throw it through and we'll get the same result, and that becomes the program. Because importantly, the the way that Ada actually set it up originally, and if you go back and you look at her notes, she's freaking brilliant. Um, I believe that she managed to program in a system to produce the Fibonacci sequence on the analytical engine. And this is important because that this was not considered to be possible, that you could take a short set of instructions, give it to a machine, and produce an ever expanding correct output. She got the idea looking at the jacket looms, which were used in English textile mills in order to produce the different patterns in fabric, and then took it to the next stage. Absolutely brilliant. And so quick shout out to Ada, mother of programming. Without her, where would we be? Jumping up to my next favorite computer scientist, Alan Turing. Uh, Unfortunately, died early of suicide. Lots of different theories on how we got there. I tend to go with the um, died because of homophobia. But Turing, mathematician, logician, crypto analyst, computer scientist. When I got to grad school and I was starting to study evolution, I'm used to seeing Turing in the computer science world, but when I started seeing Turing in the theoretical biology world, I was like, damn, this dude's smart, right? Formalized algorithm, formalized computability, the church Turing hypothesis, the Turing machine, and of course the Turing test was the first idea of intelligence within the machine. Um, so Turing's potentially most famous work these days is probably his work during World War II. The Germans had the Enigma machine, very cool cryptography setup that could not be broken by hand. except when they got very lucky on different days. But to be able to actually break it every day consistently, they needed a machine. And so Turing came up with a computational model and a giant machine called the bomb at Bletchley Park, and they were able to continually crack the enigma in order to be able to reduce the time of World War II by a few years, and save thousands, hundreds of thousands, potentially millions of lives in the process. Turing and computer science allowed for World War II to end earlier. I just think that's pretty freaking amazing, right? Problem: we got a war. Solution: here's a machine. Jumping forward to 1948, we are in the early post-war period. We're now in New Jersey at Bell Laboratories. Of course, everybody should remember that Bell at the time had a countrywide monopoly on telecommunications. And so they also had a huge research and development laboratory, Bell Laboratories, where just tons of really cool stuff came out of, um, like the transistor. When we think about logic gates, once we move past hand crank, and once we move past steam driven mechanical operators that we've just seen, with the difference in the analytical engines, we get into electronic computation. And the transistor would replaces the vacuum tube. The vacuum tube's like this big for some of them. It could be like down to this big, depending on the particular need of the machine. The transistor is like this big, so it's a huge step forward in micronization of computational possibility. Big important step moving forward. Here is UNIVAC. UNIVAC was one of the first major computational systems, if I remember correctly, U.S. military, primarily used to calculate artillery projector, artillery projection, so that you could accurately hit the target, use um, uh, fewer shells, all that stuff. Um, but this also sort of set the standard for what computation would be doing for the next 40, 50 years. A very linear process of how we approach problems, very mathematical process about how we approach problems, um, which we will get back to in a little bit. Popping back over to England, 1955. This was Turing's post World War II work, the Pilot Ace, I believe University of Manchester, and he was working on a slightly different model of computation to what was being worked on in the US on UNIVAC. Um, but around this time, I think the von Neumann model takes over, and that's what we mostly deal with today. 1958, Jack Kilby at Texas Instruments invents the integrated circuit. So instead of having to, solder together a whole bunch of transistors in a line, and gets really weird at that point, why don't we just build all these transistors onto a single board? We can just print it out. It'll be fabulous, and it was fabulous. And the integrated circuit we still use, we still love, and it just keeps getting better and better. Um, Popping by to say hi to Admiral Grace Hopper, the Amazing Grace. Admiral Hopper was an early programmer. Some people, suggest that while England had Turing, America had Grace Hopper. I'm kind of agree with that. Um, she she's a badass. She invented the compiler, even though a lot of men at the time said a woman couldn't possibly have come up with this good of an idea, but she did. She led the efforts to help build Fortran. She was one of the lead designers on COBOL. Fortran, of course, being the high-level language targeted at mathematics, COBOL being the high-level language being targeted at business. And then we take these high-level concepts, which are easier for humans to be able to program with, and to be able to reason about. We run them through a compiler because the computer is great at translating stuff. And then we turn it into, into a program to run on the machine. Grace also coined the term debugging, famously. You know, they were having a problem with the computer. They went into the warehouse where all the vacuum tubes were being held, and they found a moth that had been bouncing around between the different tubes. It was too hot in there. It was really unhappy. It was trying to get out, and so that became the first bug in the system, a moth. And if so, when you go in and you debug and pull that moth out, that's where the term comes from. Jumping forward, we've got the mainframe. I grabbed the Cray supercomputer here because it has seats. I mean, that's pretty cool. It's a supercomputer. It's a mainframe. It's got seats. And the mainframe is where the terminal, as we understand it, comes from. Because there was a big central machine, and we would have a whole bunch of wires coming out into dumb terminals. There was no computation happening at the terminal, so it would take inputs from the user and then send this off to the mainframe, and then the output would come back and pop up on the screen, right? So it's a terminal. It doesn't actually do the computation. It time shares with the other users on the mainframe. Pretty cool. Hugely expensive. Took up a lot of room. Took up a lot of electricity, and was entirely unacceptable for a lot of what we would now consider computational uses. So now we pop into the Apple personal computer, right? This is the big attempt to get computation into the house. Being able to get computation onto the desk, created by the great and powerful Steve Wozniak. Wozniak, I would like to just give a quick shout out to, because he's the guy that came up with the first affordable chip for controlling color monitors. Wozniak's work is a direct link to us being able to talk in color on our monitors today. I mean, cool stuff. The personal computer. This was actually my first computer. The came out in 1981. The IBM personal computer, running on the Intel 8088 CPU architecture. I had a clone. I couldn't afford the real thing, but still cool. And as we all know from here, we jump forward through the 886, the 286, 386, 486, up to the Pentiums and into the CPUs that we've got these days. So at the same time, people started to figure out, these mainframes are hugely expensive, right? And you know, what they're good for, they're very good for, but they're not very good for a lot of things that particularly need cheaper computation, or really just don't need that much of hardware. And so, we can start to look at these cheap personal computers, and we can say, oh, we could just like use one of those and just run some software on it, and over the network, we can access it and thus the server is born. You know, Relatively cheap, dedicated, machines. It was a great, step forward in computation and the availability of computation, particularly for businesses. A business that could not afford a mainframe could definitely afford a server, and then they would just need, the desktops to be able to interface with that server. So much cheaper than a mainframe and all the dumb terminals that you have to deal with. Also cheaper on the IT end of things. They're a lot easier to fix. So the virtual machine actually was originally an idea for the mainframes. Time sharing the system between different tasks, which was necessary at the time. But coming forward into the realm of the server client architecture, and a lot of servers have a very specific role in what they do. They don't do anything else, and this leads to a lot of wasted hardware and a lot of wasted cycles. If you've got a web server that's only running at 20% capacity at any given point, that's 80% of your computer is being wasted. And so the idea of the virtual machine was brought forward into sort of the server architecture of everything, where we can now share the actual metal between a couple of different servers. And so, we'd have this physical machine, we'd have some sort of virtual machine management system. I first started with the SX back in early 2004, 2005. Um, when I was virtualizing machines for Vodafone, it was a great step forward in being able to concentrate and bring down costs for larger computational projects without having to sacrifice the individuality of the individual servers, which, as we all understand, capitalization is good because it stops unwanted interactions between different programs on a computer. However, we eventually figured out that hosting an entire host operating system is actually still, again, quite wasteful, and so we step into containerization. The big difference between the virtual machine and the container, as we all know, is that we just get rid of the guest OS, right? We only use the minimal set of code actually required to run our containers. Very cool, big step forward. But this also means that now that we've got rid of the guest operating system, we can actually fit a lot more stuff on the individual pieces of metal that we've got access to. And now that we've got tons and tons of containers, how do we orchestrate them? And that's why we learned Kubernetes. That's why we learned the different orchestration systems, because we've got all of these machines, which originally, back when I started in IT, it was one machine, one operating system, probably one service. Now I've got one physical box can have up to what, tens, hundreds, depending on the size of the container, on one machine. And back when I had to take care of 400 physical machines, that was hard enough. But having to take care of thousands of containers, having to take care of millions of containers, that is not something that a human can effectively do. So we tell the computer to do it for us, and that's how we get to Kubernetes. Any questions? All right, I'm going to say that it's no questions. Thank you all very much for your time and attention, and I'm going to stop the recording while David gets set up.